So, anyways, wow, cool morning today. Really very cool. Oh, hello. I'm not very late. Really nice. Okay. Okay, let's start things off this morning. Okay, so today we're gonna go over acid base. I know some of you guys have technically done acid base in school already, but we're gonna do this whole thing one more time, okay, because it's been a while. Okay, so just to start things off, okay, for acid base, right? Okay, I think usually, right, I take about 4 lessons to cover this, including the tutorial. Okay, but based on our planned curriculum, right, we can only afford 3 lessons. I think last year maybe Krishan can remember, we went through maybe about 4 lessons with this. Can't really remember exactly, okay, but we have 3 lessons, meaning to say this one will be quite tight. Okay, this topic, very big, very crucial. Okay, so let's start off with this. Okay, today, right, okay, the concepts we're gonna learn are very similar to the ones we've learned in secondary school, but we're going to dispel some myths that we have learned before this. So some of the things that we have learned regarding acids and bases in secondary school are not going to be entirely true in JC. Okay, so that's the purpose of today's lesson. We're going to look at the basics. Okay, so maybe today we're going to look at ideas of pH and pOH. Maybe about that, okay, but of course there are other measures and all that. Okay, then the next lesson onwards, right, the intensity is going to ramp up. Okay, today we are just going to look at all the fundamentals, right, which we need to know before we can move on to the next lesson. Okay, so I just need you guys to take a look at the first page. Just on the first page alone, okay, you can see there's a bunch of different weird names. Now, when I ask you guys a very simple question, right, okay, what is your association with an acid? Okay, some of you guys take a look at an acid, and then you guys will think of H plus, right? But in secondary school, when you all take a look at the base, you all think of what? What do you all think of when you all look to see a base? What does it give? Okay, it gives OH minus, right? Okay, so you're not entirely wrong over here. But in JC, right, this is also known as the Arrhenius theory of acids and bases. And I can safely say that they will not explicitly test this guy's name all that much. Because most acids and bases in JC, right, will be this other formula here called the Bronsted theory. Okay, the full name is called Bronsted-Lowry. Now, why do we have other theories? Okay, I hope you all just understand, right, that in the entire world, we cannot cover all the definitions of acids and bases just based on this one guy's theory. Okay, some other species can also exhibit acid-base properties. If, okay, in the Bronsted theory, it says this, if a species is able to donate a H plus ion, it can also be considered as an acid. Okay, as for Bronsted base, if you can accept that H plus ion, you're considered as a Bronsted base. At the end of the day, it is still considered a base. It's just that now we are trying to expand our library of acids and bases. It's not just H plus and OH minus. Okay, there could be overlaps. Later I'll show you guys examples. Okay, or in fact, let's just look at a simple example now. One of the most common examples we're going to use in this topic is this guy over here. Okay, as you all know, this is ethanoic acid. We'll be writing this guy's formula over and over again. But let's just react it with a base, which is like OH minus. A very, very simple acid-base reaction, correct? Okay, but what's going to happen here is this. I just need you all to tell me, this acid over here, what does it become? That's okay, no worries. Okay, what happens to this acid over here? What does it become after it neutralizes? Okay, so based on either of the theories, right? If you say that this is an acid, it can be either the Arrhenius acid or it can be the Bronsted acid, right? Okay, so what it's going to turn into, right, is this CH3CO2 minus. As you guys can probably see, it has donated already its H plus ion. That's how it becomes this guy, the salt. Okay, later we'll look at what the salt is called. Okay, but at the same time, this guy, OH minus, is going to become water. Because as we all know, acid plus base gives you salt plus water. Okay, this right here is the most fundamental acid-base equation you guys have learned before, right? Okay, but you all can see based on the definitions that this works. Okay, this is a Bronsted acid because it donates away the H plus. But at the same time, guys, can you all see that this is a Bronsted base? Now, this base, obviously, okay, even though it's just OH minus, he accepts the H plus to become water. So you can see they are partners of each other already. Okay, so some of you all might be very familiar with the terms and all that, but never mind, okay, we'll go over that on the next page. Okay, but as you all can see, right, because we have different types of acids and bases, we need multiple theories to cover everything. So on top of all this, okay, we have our final theory, right, which is the Lewis acid-base theory. Okay, this one over here, okay, I'm going to give more examples. But as you can see here, right, Bronsted theory is about protons. Okay, H plus is also known as a proton. But Lewis theory is about electrons. Perhaps that's one way you can use to memorize this. Okay, you guys need to know the definition by heart, because they can test as a 1-mark question, and all you need to say is Bronsted theory donates H plus or so on and so forth. Okay, on the other hand, guys, if you go take note also, a Lewis acid accepts a pair of electrons. A Bronsted base, as you can probably guess, donates the electron. If one guy accepts, the other guy won't donate. Okay, you just need to remember who is who. Now, I'm gonna just clarify this. I'm gonna preface this. In this entire topic, our focus is on Bronsted theory. Okay, I say this again. On the next page, you will also see something about H plus. Okay, this whole topic focuses on Bronsted theory, but okay, because Lewis theory will carry on to other topics, we're going to look at a few examples. In fact, anything to do with electron transfer is quite familiar to you guys already. Perhaps I can give you guys this example. Okay, if I take NH3 and I react it with BF3, I will just get this compound over here, NH3BF3 combined. This reaction over here, right, okay, is very similar to something that you have learned in chem bonding. If you can just tell me what it is. Okay, you all take out this example also. Some of these examples not in the notes. Again, I expect you guys to write it down also. Okay, but what's this? How does this compound form? As you all can see, right? NH3 just somehow combines with BF3 for some odd reason. Okay, but you all know what this bond is between NH3 and BF3? Any guesses? Okay, or perhaps I give you a bit more clues. Okay, there's a bit of electron transfer in this case. Ammonia in this case has that lone pair of electrons. And somehow it can use the lone pair of electrons and give it to BF3. What kind of bonding is this? Can you remember? Okay, daily bonding, yes. Okay, so this compound is formed via daily bonding. But if they were to ask, what is the type of reaction? You can't just say a reaction type is called daily bonding. Can you see it doesn't make sense? Okay, that's why if they ask for type of reaction, you must tell me Lewis acid-base reaction. So yes, I know this doesn't look like a conventional acid-base equation, but it is still considered one because of the Lewis theory. So all we are doing on this page is expanding your worldview on acids and bases. Okay, so it's no longer just a very simple equation that you see up here. Okay, not to say that it's wrong. Okay, let me just remove this. It's not wrong. Okay, we're still going to encounter this, but they are mainly going to test on Bronsted and Lewis. This topic alone will be focused solely on Bronsted. All okay so far? Can Alright, okay, so as for definition, right, this one, there's no easy way to remember it, just remember it. Okay, so I mean, the easy way is Bronsted is the protons. Lewis was the opposite of proton, electrons, then the accept and donate. Okay, you all can go remember this. All good so far? Okay, but never mind, by the end of this topic, you will know who's Bronsted acid and who's Bronsted base. Okay, you can turn over to the next page. Okay. Okay, next page is ultra important now. Okay, so basically, again, this whole lesson, we are setting rules in place, and then we can use these rules for future lessons. Okay, so we're going to understand, right? What is a conjugate acid-base pair? Now, of course, the definition and all that is there, okay, but that's not my point. Okay. Now, as you can see over here, a conjugate acid-base pair can be seen in this equation that we have already shown just now. You might even see that in your notes also. Okay, I'll give you guys more examples, not to worry. Okay, we're going to reuse this definition over here, this equation over here. Okay, so first of all, what does a conjugate mean? Okay, a conjugate just means, okay, in simple English, a partner. Okay, perhaps you can take note of that. Again, it is not the formal definition. The meaning of conjugate, if you search in the dictionary, right, they give a lot of weird meanings. Okay, but in terms of chemistry here, you can think of it as a partner. Okay, so they exist as partners over here, that's why it's a pair, right? Now, I need to establish a few facts first. The most important thing, number one thing you must always take note. to identify a pair, they must differ by only one H plus, nothing else, only one H plus. Core idea. Today we're going to be practicing this, see whether you can identify a pair. But I'm going to add another information. This one's already been used. Okay, but another piece of information that can help you guys is this. The acid always has one extra H plus. Okay, because if there's an acid, there's going to be a base pair, right? The base, conversely, must have one less H plus. Okay, acid is always the one with the extra H plus. Okay, you guys must really pay attention to these two rules. Then you will never go wrong with your identification, never. Okay, we can also take down this example that we took down in the first page. Okay, because I think this page they gave a slightly different example, not to say that it's wrong. Right? So as you guys can already start to see, we are talking about H plus, which is basically your constant theory. Coming back to this equation that we saw just now, okay, can you guys just identify first who is the acid? Very simple, right? The acid is just your anthropic acid. But guys, who is its partner? Okay, I'll use this word first, later I will change the word to conjugate. Okay, so who is its partner over here? Very clearly, you all can see is this guy over here, right? Because he only differs by one H plus and nothing else. This is known as the conjugate base. Just now, we used the term salt. We're going to slowly phase that out, even though yes, it's still relevant, okay, not to worry. It's a conjugate base. Meaning to say, they are partners of each other. You want to highlight, you want to draw arrows or whatnot, they go ahead. They only differ by one H plus, nothing else. And just to prove my point over here, the acid is the one with the extra H plus. The base has the guy with one less H plus. Now, on the other hand, if you take a look at OH minus, what is this? Okay, if there's an acid, you must react with a base, okay, obviously. Okay, so you see OH minus, everyone thinks of base, you're not wrong. Okay, but who's its partner in this case? Water. Can you see water compared to OH minus has one extra H plus? So guys, will you tell me what's the term for water in this case? Acid and conjugate base. So base and conjugate acid. Now guys, the word conjugate doesn't actually hold that much weight. It just means it is the partner of the base. It's to tell you who's the partner of that. You can see that. Okay, so nothing special here. Okay, conjugate just is it's just a just a label. It's not really, it doesn't hold that much meaning. All right, and so far. So yes, okay, we're gonna look at more examples. Okay, the one in the notes I also can go through. Okay, in the notes, they went through this equation here. Okay, same thing, ethanoic acid. This time round, it dissociates in water to produce these two speeds. Now, I want to talk about two equations that are very, very similar. Okay, so I'm going to write a similar equation, right, in the notes. Okay, if I'm not wrong, the notes only has the first equation. Okay, you all take a look at the second one as well. Both equations are the same thing. Okay, they are the same. So it is up to you guys to write whichever one you want. Okay, but let me explain first. Okay, you all take a look at the second equation here. Okay, as you can see, this is an acid. So who is its partner? Okay, clearly is this guy, conjugate base. Now H plus is just whatever it is associated into. Now can you all see, right? It's an example of an equation that fulfills both theories of Arrhenius and Bronsted. It donates a H plus, yes, but at the same time, it produces a H plus. So you can see it's not exclusive. The definitions can overlap, but it's not a big deal. Okay, it's still an acid at the end of it. Makes sense? Okay, so as you can see here, guys, there's only one partner. We can do the same thing for the top equation that is already written in the notes. This is the acid. Okay, you all just follow me first. This is the conjugate base, correct? Now, what is water in this case? What is water? If CH3CO2H is an acid, water is a base. Now, as counterintuitive as this is, yes, water can act as a base just from this definition over here. You all have to look at the definition solely. That a base is something that can accept an H plus. As you can see, it accepts the H plus to form H3O plus, which is its conjugate acid. I know some of you guys may be thinking, hello. Welcome. Oh, you can see. Let's see in front of the camera. Okay, so as I was saying, guys, a base, I know you guys are still kind of clinging on to the idea that a base gives OH minus, but no. In this case, can you all see, does it give any OH minus? No, right? But as long as it accepts an H plus, it is still considered basic. Again, of course, its partner you must go and identify. Later we'll do all this, identifying anything over here. Okay, I'll come back to this in a bit to show you guys that these are two same things. Okay, y'all can take note first. H3O plus and H plus, they are the same. It depends on whether you add the H2 at the start. Okay, okay, so we have established quite a few important things to carry on into the next few pages. All okay so far? Yeah. Okay, so I already explained everything on page 3. Okay, on page, or before we go over there, right? Okay, let's take a look at page 4. I'm only going to look at the second example. Okay, we don't. The first example you all can probably try yourself. Okay, now the second example here is for ammonia. Now, just perhaps maybe do me a favor, right? Change the arrow to a reversible arrow. It will eventually make sense when I go over the next few pictures. Okay. Now, okay, go and identify the S. Okay, you just need to name them. We're going to encounter a few very common species in this topic. Okay, the first common species, as you guys have already caught on, is ethanoic acid. Okay, this guy is a very common acid we're going to use, and a very common base that we're going to use is ammonia. Okay, so ammonia is probably the main base you're going to use for this topic, but of course, they can come up with anything. Okay, the point of this exercise is just to identify conjugate pairs, right? Okay, so going by the rules, okay, this is our answer. Okay, so if this is the base, the conjugate acid must be NH4 plus. Because once again, you go and check out, they differ by 1 H plus only, nothing else. And the NH4 plus has an extra H plus. So that's why it's the acid, going by my rule over here. Okay, so far, all good? Okay, and again, conversely, water now can act as a what? Acid. If he's the acid, then OH minus must be his conjugate base. So guys, I want you guys to take note. Water in the scenario just now is acting as a base, but now it's acting as an acid. It actually depends on the context. So don't cling on to a certain species and just memorize it as a base. No, you confirm go wrong. In this context, it's an acid because you're going to check out. When it turns into its conjugate base, the base has one less H plus. The acid has an extra H plus compared to this guy. So it still fulfills the two criteria. Okay, so far. Okay, so you can try the first example yourself, okay, but it's pretty much the same thing. Okay, now I just need you all to turn over the page. Fine. Okay, so you guys have seen this page in secondary school, definitely. And in JC, it's not that different until later. Okay, so strong versus weak acids and bases. Okay, so a strong acid can dissociate completely in water. Okay, to produce H plus. Okay, you can see the definition, it says that H plus or H3O plus. Should be quite obvious over here. Right? Same as secondary school. Now, guys, what's the arrow that you use if you want to dissociate a strong acid? Full or reversible? It should be full, right? Okay, because you dissociate completely. So all of your acid must turn into its ions, whatever. Conversely, you look at the weak acid definition, it only dissociates partially in water. Which means you have a reversible arrow. Okay, good. And guys, remember, in this topic, it's called acid-base equilibrium. So the word equilibrium already implies that we are going to use our reversible arrows for most of this topic. In other words, okay, you won't really see calculators for strong acids that much to that extent. Okay, you like pretty much virtually won't see it at all. Okay, so just pay attention to that. Now there's another detail that I want to talk about, which I will come back later on in the lesson. Okay, if you look at under strong acids, they say this. Okay, I just look at HCl, very common strong acid. Okay, full arrow to form into H plus and Cl minus. Okay, now first of all, okay, since it's not written over there, go and identify the conjugate pair first. Okay, you all should know that acid is HCl. Who's its conjugate base? Sorry. Okay, good. Cl minus, conjugate base. They differ by 1 H plus. Okay, so that's a pair. Now, take a look first. In the notes, they said something along these lines. Okay? HCl is a strong acid. Cl minus will be a weak conjugate base. Conversely, if you were to take a look at a weak acid like this guy here, up here, he is a weak acid, which means you will produce a strong conjugate base. So this is covered in both the top and the bottom. As for now, you guys don't need to know why it's opposite, like one weak, the other one will be strong, and vice versa. Later, I'll explain that. But for now, I just need you all to understand the logic, the intuition behind this. Now, guys, we talked about full arrow versus reversible arrow. If this is a strong acid, the reaction is lying towards left or right. I mean, based on the full arrow, it's lying very heavily to the right? Now, because he is a weak conjugate base, do you think he will attract the H plus to form back HCl? Can he attract back the H plus to reverse the reaction? No, because again, it implies that he is a weak conjugate base. He can't go backwards. On the other hand, if you take a look at this guy, because this conjugate base is very strong, he can very easily attract back the H plus and reverse the reaction. Does that make sense? So that's why you can think of it this way. This guy is fighting back. That's why there's a chance he can fight back the reaction. He can resist. Whereas for this guy, he's like, he already give up on life already, right? Okay, he already associated into Cl minus, but he doesn't bother to go back because he knows he's going to lose anyway. Okay, so you can think of it this way. The strong will dominate, then this guy will try to fight back because he thinks he's stronger than this guy. Yeah, it's kind of like a fight. That's why it's like reversible reactions. Okay, so that's the idea. As for why it's opposite, why one weak, one strong, later we'll talk about it. But now just understand first. So that's why this is a weak acid, because he has something trying to fight back his dissociation. This guy, he doesn't care, so he very easily can dissociate from. That's the intuition behind it. Okay, understand that first. Okay, let me erase some examples. We'll just have to focus on those. Can so far? Can Okay, so now that you have kind of understood strong and weak, let me just ask you guys a question. In secondary school, when I tell you guys strong acid, is there some sort of indicator that tells you that acid is strong or weak? What's the indicator called? Okay, I'm not talking about like, the titration indicator. Okay, if you think of a strong acid, you think of, how do you measure the strength of an acid? pH. Okay, that's what you guys have been taught. Okay, so pH measures the strength of the acid. If a strong acid must have a high or low pH? Low, about 1 to 2, right? A weak acid has a pH of around what? About, okay, maybe not 3. 3 is still considered okay, mild. Okay, about 4 to 6, around there, right? Okay, now we're gonna start to realize that this is actually wrong in JC. Then why were we taught this in secondary school? Okay, later all the answers will come to light. But for now, I want you all to take a look at page 6. That's what they're trying to clarify. Now, you all see at the bottom of page 6 is full of, it's a big box of, there's a lot of blanks on page 6. Later, I need you guys to write down whatever I write on the board for page 6. As of right now, I just need you all to understand first, pH is not a good indicator for strength. We will understand why. Okay? Now, we will come back to page 6. So let me tell you guys what we're going to do now. We'll go over to page 7 to learn some very basic equations. And then later we'll come back to page 6 to write some examples to prove this point. This part very important. Okay, so come, let's go over to page 7 first. Now you guys know pH, that one secondary school we learned before. Okay, but pH, right, in JC we can actually perform some calculations. In secondary school, all they've done is to tell you pH is 2, pH is 4, pH is 5. Yeah. Okay, so pH is a formula actually. It's negative log of the concentration of H plus. Okay, so just look at this equation. I'm not going to teach you guys logarithms. So H plus, if you want to find concentration of H plus, you take 10 to the power of negative pH. That's just how it works. Okay, you want to write some examples, go ahead. So if I were to tell you guys this, okay guys, if the pH is 2.14, how do I calculate the concentration of H plus? Okay, 10 to the power of negative 2.14. Why negative? Is because it's negative log. Okay, so same idea here. P stands for negative log, base 10. Okay, and in other words, guys, if you guys just realize pH is just to measure the concentration of H plus ion. So that's why it can be used to measure, a lot of the times we use to measure acid strength. Because guys, you think about the logic first, a strong acid gives high or low concentration of H plus. Strong acid, high or low concentration. Probably high, okay, because it dissociates completely. And then a weak acid probably gives low concentration. So as of right now, on surface level, it looks like it's a good indicator of strength. Okay, but hold on for a second. Let's look at can you write down this small little question now? Okay, that I'm going to pose to you guys. Now, is it possible for pH to be negative? Now, for your first answer in your head would probably be no, because it's not like we've encountered this before. But now that we have learned the definition, I want you to can you like take out a calculator, maybe punch around some values and perhaps try to get a negative pH out. Okay. If it's possible, you can tell me what should the concentration of H plus be such that you can get a negative pH. If try to because I'm telling you this right now to really understand the formula, right? How do you get a negative pH? Okay, so however you're gonna do that, right? Just maybe play around with some values. Okay, good. So what you have done is this, okay? You have probably chosen a negative pH and then you work backwards, right? Okay, I mean the two equations are there. Yes, if the H plus concentration is more than 1, you will get a negative pH, not because of magic, but just because of the negative side. That's just how the math works, nothing special. Okay, so yes, because this came out in the Nanyang JC paper of last year. So what happened was this, even my two students, they got a negative answer. And pretty much half the school went to change their answer because they thought they were wrong. But actually they were correct. So they cannot penalize. So I just want to warn you guys this first. Nanyang JC have tested negative pH. And it's possible. Okay, do not think that you're wrong. Okay, trust in us. Okay, and guys, how do you get a pH of 0? So, in secondary school, you have been taught that pH lowest is 1. But can we get a pH of 0? What? Okay, for pH to be 0, pH plus concentration must be equal to 1. Yes. Okay, so you have 1 mole per dm cube of H plus. Okay, then your pH is 0 lah. Okay, again, our pH is not some magical number that stops at 1. No, okay, it can go to like literally any number as long as your concentration of H plus is legit lah. Okay. So acknowledge this first. So in future, do not doubt your answer. Alright? It can go below 1 now. Next. When there is pH, H meaning H plus, there's going to be POH. Okay, so POH is related. Okay, it's just a measure of OH minus lah, really nothing special. Okay, concentration of OH minus, then you want to find, again, I just write both, 10 to the power of negative POH, blah blah blah. Okay, you're gonna get some values also. Okay, same exact thing. You can get a negative POH also if you want to. Okay, but most importantly, right, at the bottom of this page, there's this equation. pH plus pOH equals to 14. You guys probably have heard of 14 before, right? Okay, if the pH is 14, it implies what? Okay, pH 1, strong acid, pH 14 means what have you all been taught in secondary school? pH 14, very, very high pH means strong base. Yeah, okay, so that's what we've been taught before. Okay, but I want you all to circle out the 14. It's not some special number. This 14 is only at room temperature. Sometimes room temperature you can see it as 25 degrees Celsius. Okay, so yeah, pH plus pOH equals to 14, but pay attention to this. At different temperatures, you can get 15, 16, 17. We'll come to that later. Most of our calculations, thankfully, are at room temperature, so we shall mostly stick to this. But later I'll tell you all when it becomes different. All okay so far? Now that we have understood pH or pOH, turn back to the previous page. We have to now understand why this box even is in the notes. Okay, over here, it doesn't explain much, so I need you all to write things down. Okay? Now we're going to understand, okay, as I told you all just now, pH is actually not a good indicator of strength. Why? Let me present to you all a few scenarios. Okay, HCl, strong or weak acid? Strong, right? Everyone knows it's strong, it dissociates fully. What does it mean to dissociate fully by definition, right? Okay, go and write down an initial, change, and final. Let's use numbers. Guys, if I were to give you HCl as 1 mole per dm cube, sorry, let's not use 1 mole. Let's use 0.1. Okay, initially you don't have any ions yet because the reaction hasn't begun. But guys, what is the change in this case? Okay, strong acid dissociates completely. So at the end of the day, how much acid must you have? 0. So meaning, as you can see, completely means all react. How about the right hand side? What should we do here? Add how much? 0.1 as well. Okay, remember why? Because your change must follow what? All of your change must follow mole ratio. This one applies to your chemical equilibrium as well. It applies to solubility equilibrium. Just look at this, all 1:1 ratio. Now, why I have to focus on this is because in the previous class, someone tell me this. If this one dissociate by 0.1, this one plus 0.05, then this one also plus 0.05. That's just not how chemistry works. Okay, in chemistry, just follow the mole ratio. 1:1:1, can already. Okay, now of course over here, this is a very simple table. And guys, can you all just help me calculate what is the pH of this scenario here? Okay, what's the pH? Okay, now that we've learned the definition of pH. Case 1. Okay, so how do you calculate it? Very simple. Negative log of 0.1. Where do you get 0.1 from? Right here, right? This is the concentration of H plus after it is dissociated. So you get pH of 1. Oh look, it looks fine, right? Guys, a strong acid has pH of 1. Perfect. But now repeat the same table. Go and draw out the same exact scenario. And I want you all to write this value inside. And I want you all to complete the table once again. And after completing this table, can you all go and calculate the pH form? Just gonna dissociate everything, so left with 0. Right hand side, you plus the same values, plus this. Okay, what's the pH in this case? 4. Okay, just now I thought we said that pH 4 is weak, right? Did we not say that? Okay, so guys, can we now conclude that HCl is a weak acid? Is HCl a weak acid? No, guys. So can you see? I can just change the concentration of the acid, and then I can get a totally different pH. But is my conclusion accurate? No, because as you can see, you're going to write down this like question to yourself. Does this mean HCl has magically become a weak acid? Okay. This is a rhetorical question because you guys probably already know the answer. You should know the answer to this question. So you can see there's a flaw with using pH to measure strength. Strength just tells you the whole thing dissociates. But guys, can you see I can have a super duper diluted acid and I'll get a slightly higher pH. So this is a scenario in which I can have a strong acid but that is super diluted. And then my pH will not give me accurate information. Right? Okay. We're going to look at a converse scenario. Okay, I'm going to now use a weak acid. Okay, you all can take down first. Okay, we will look over at the next example. We'll look at the dissociation of a weak acid. And we're going to write down another table. So try to leave some space for this side also. Right? Okay. How do you know that this is a weak acid? Reversible arrow, correct? Okay. Now let's just say that the concentration of this weak acid is 1 mole per dm cube. Will all 1 mole per dm cube dissociate? Will the whole thing just change, become 0 at the end? Yes or no? No, right? Okay, why? This is a weak acid. A weak acid only dissociates a little bit, so you're gonna have leftovers. Agree first? Now, guys, how much does it dissociate? Do we know? We probably don't know for sure, but let me give you an assumption. Okay, so you can write this at the side. Assume only like 10% of the acid dissociates. Of course, this is not true in real life. In real life, there's a way to calculate this. Later, we will do that. But as of right now, can you all just tell me if 10% dissociates, if 10% dissociates, then what's the change? Minus how much? Okay, this one you must know how to fill up. Okay, the word 10%, what does it mean in terms of this table? Okay, is it minus 0.9 or minus 0.1? Okay, good. You only minus 0.1 because C, the change, stands for how much dissociates. Okay, so if only 10% dissociates, you're left with 0.9 of the acid at the end. And I want you guys to fill in the rest of the table. Okay, this is just based on this assumption to prove a point. Okay, my point that I'm trying to prove is this. The whole thing doesn't dissociate, only a small portion. What's that portion? Let's set it to 10%. Okay, so 10% dissociates. Okay, 10. So what's the right hand side of this table? Should be quite simple. You just follow mole ratio. So 0.1, 0.1. Guys, can you all calculate what's the pH in this? You all notice the concentration of H plus here is 0.1. If we negative log that value, you're going to get the same answer as above. And we're going to write down the same rhetorical question. Does that mean that ethanoic acid is strong? Then pH 1 what? Correct what? Strong lah. No, okay, that's not accurate. Okay, so does this mean, okay, just write that down also. Does this mean CH3CO2H is a strong acid? Again, a rhetorical question because you know that this is a wrong statement. But using these 2 points, I have already proven that this is a flawed way of measuring strength. pH from now on should not be a way of measuring strength. You should throw this idea out of the book. Okay? So why would you thought this in secondary school is because it's a very basic introductory level. But you can see over here now, this is the main idea. At the end of the day, pH is just a measure of concentration of H+. Please write this down. It just measures how much H+ you have. Okay? And because of that, that's the drawback of pH. Okay? The limitation of pH is this. You can write this down also. It depends on how much your concentration of acid is. It doesn't matter whether it's weak or strong. I can put any concentration to get any value of pH. That's already a flawed system. Again, this is a scenario where I have a weak acid that is very concentrated. Just these two scenarios alone already invalidates pH as an indicator for strength. You see that? Okay, so always go back, really study this portion also. You're right now, it's not for fun. Okay, when you study the notes, don't ignore this portion. It is relevant. Okay, I'm doing all this, okay, so that later on, you all can really understand what is a better indicator for pH. What's a better indicator for acid strength? This merely measures concentration. Bad, okay, no good, not reliable. Okay, any questions so far? Okay, if you have any questions, please ask for this part. It's to really get you guys into the zone here. Okay, all good. Okay, if all is good, you can now turn over to page 8. And on page 8, there are some formulas you can remember. Okay, but you see the box at the top of the page. Okay, let's answer this. Okay, see whether you can really understand the idea of pH. So, does the concentration of H plus half when you increase pH from 1 to 2? Okay, 1 to 2 is double mark, so the pH, the H plus half, right? Is that correct? Okay, so if you think it's wrong, okay, then how does this work then? Perhaps let's not use pH as a scale. Okay, let's convert pH into something we're more familiar with, which is concentration of H plus. Guys, can you tell me what's the concentration of H plus when pH is 1? It's just 10 to the power of -1, right? Then pH2 is just 10 to the power of -2. As you can clearly see, when pH increases, how does the H plus change? How does it change? Is it twice? Okay, no, it's not half also, right? It is 10 times smaller. So you need to recognize that this is a logarithm, I can't pronounce it, log scale now. Okay, it's logarithms. So it is 10 times. Okay, you can write that down also. Okay, of course, they won't test this in the exam, it's just for your own information. Okay, so the concentration of H plus decreases 10 times. Okay, when pH increases from 1 to 2. Of course, write down the conversion also, don't just write down the statement, because when you look back at this 2 days later, you'll probably forget why it's 10 times. Right? Doing okay so far? Yeah. Right, we look at the next part. Okay, so we're going to introduce this constant capital K called Ka. Now, as we have seen before, we have seen Kc, we have seen Kp, and just like all the other Ks, it's just another equilibrium constant. Ka stands for acid, very simple. Okay, and to write down this constant, okay, you guys must first understand that when we have an acid, we're going to use a generic form from now on. It doesn't matter what the acid is, we can just call it HK. Because no matter what, when you dissociate this thing, what does it become? Who is his partner? What's his partner called? Acid must give you a conjugate base. What's the conjugate base formula in this case? A minus, good. Okay, because if we follow our criteria just now, he has one less H plus for the base, and they must differ by the H plus, right? So that's where you get H plus in return. Now in the notes, they might also write this down. Acid dissociates in water to produce a conjugate base and H3O plus. As I've mentioned, H3O plus and H plus is the same thing, but what's the difference? The difference is only based on whether you choose to add water on the left side of the equation. It's just for the sake of balancing, but they are the same thing. Okay? Perhaps I'm going to use the bottom equation, right, to write down the K expression. Now guys, when you write any K expression, right, what's the format? So it's what divided by what? Reactants over products or products over reactants? Okay, so it's products over reactants, right? Good. Okay, so let's use the bottom statement. Okay, products are here, right? So I have A minus H3O plus or H plus, you want to write whichever is fine, over what? Reactants here are HAN. Okay, is H2O part of the Ka? If you take a look at the notes, it is not. Why is H2O not part of the expression? What is it acting as on the left-hand side of this equation? It's just dissolving the acid, right? So it's acting as a solvent. A solvent must be present in what? Is it a lot or very little? You want to dissolve anything, do you put more water or do you put a lot, very little water? A lot, right? Okay, so the solvent is always present in large excess, meaning to say, you're going to ruin the expression if you choose to put it in. Just a bit of FYI, water has a concentration. I know it's a bit hard to fathom that idea. Water has a concentration of 55.6 mole per dm cube. And based on the values that we usually deal with are 0.1, 0.01. This is a very large value. There's a way to calculate this value now, okay, but for now we don't look into that first. Okay, so water is very concentrated. If you put it in the Ka, you're gonna screw up the entire thing. Okay, so let's not put it in. Can? Okay, can. Now, take a look at this expression here. Okay, so this is products over reactants. Okay, that's fine. But what's most important is this. Just like all the other equilibrium constants, Kc, Kp, Ksp, now we have Ka. All these guys share one similarity. So from now on, when you all study, it's very simple. Anything that has a capital K, what is it only affected by? It's only affected by temperature. Good. Meaning to say, guys, if I were to change the concentration of the acid or the ions, will it change the expression? No. Take note of this. I can change the concentration however I like. But because this is an equilibrium system, it will shift left and right until it ensures the equilibrium constant remains the same. That's just how the system works. Okay? Now guys, you all realize just now the problem that we're faced with? Because we can change the concentration of the acid, it's not a very good measure of the strength of an acid. But now, does the concentration affect Ka? Does concentration affect Ka? No. If the concentration doesn't have a part to play, can we use it as a measure of strength? Yes. Because if you realize, I've already solved the problem that I had just now. Once again, the problem that we were discussing is this. pH is bad because the concentration affects the pH. It's not the strength that affects the pH. But now that we've taken away the concentration factor, it is purely a measure of strength. How does it measure strength? Okay, come, let's take a look at the top equation. Let's remove this. Yeah, so you can take this down at the side also. Ka is not affected by concentration. So going back to our problem just now, we've already eradicated that. So it is a good indicator of acid strength. Okay, the problem was concentration. We shall get rid of the problem now. Okay, so we get something like this. Okay. Now, as for why and how Ka is a good measure or not, we're going to discuss two scenarios. What happens when we have a high Ka versus what happens when we have a low Ka? I could just tell you guys to simply read the notes out, but no, I want you guys to understand why. Now, if you have a high Ka, take a look at the expression. I'll look at my board first. High Ka means you have more products or more reactants. Numerator, right? You should have more products, which are the ions. If the right-hand side has more, that means the position of equilibrium must have light to which side? It must have light to the right to produce so many ions, right? Okay, so if you lie the equation to the right, you are dissociating the acid, agree? So is this a stronger or weaker acid? Stronger. Yes, okay, we already said a stronger acid dissociates to a greater extent. In this case, a higher Ka means higher extent of dissociation, as you can see, position of equilibrium lying to the right. So you get a stronger acid. Very intuitive idea. That's why Ka is a very nice indicator. High means stronger, low means weaker. Why does low K mean weaker? Okay, you all can write down later. Just take a look at the second example first. If you have a low Ka, it means you have more products or more reactants. Small value. Means you have more reactants, right? If you have a lot of the reactant, the left-hand side, does that mean it dissociated a lot or very little? Did it dissociate by much if you still have so much acid? No, it dissociates by a bit only. So if it dissociates by a bit, you can say that the position of equilibrium lies towards the left. Is this guy doing his job? Is he dissociating? No. So that's why this is a weak acid. So this is what's happening here. A low Ka implies a smaller extent of dissociation because the reaction lies to the left. And it implies it is a weaker acid. From now on, you don't even need to rationalize this in your head. From now on, right, you just need to know higher means stronger, lower means weaker. Okay? So they also mentioned it under the properties of Ka. Value of Ka indicates the extent of dissociation. So they highlighted the word extent, you can highlight that as well. All good with this? Okay. Then with that, right, then the next page, very simple. Okay. Okay, on the next page, we have base law, right? Again, we have acid, we confirm that base. And same thing as before. Let's come up with a dissociation equation first, so we can come up with the expression. Okay, Kb, how do you write Kb? Now, first of all, can you see, right? Under acid, I could choose whether to add water on the left-hand side of the equation or not. But for base, I'm going to use B for base. Can you tell me when it dissociates already, what's the partner called? Okay, so hold on, let's work this out. The moment I change the symbol, then you guys will be a little bit less able to get a partner already. Okay, if you have base on the right hand side, you're supposed to get what? You're gonna get a conjugate acid. And how does a conjugate acid look like? Yeah, okay, you just have to add a H plus to the B, right? Because they differ by one H plus and acid must have one more H plus. So this is BH plus. That's it. Later we'll have an exercise where you will see wonky looking bases, wonky looking acids that you've never seen in your life. But again, fundamentally, does it matter? No. As long as you stick to these two ideas, right, you can get any conjugate base pair. Okay? All good? Okay, so let's take a look now. If this is a base, this is an acid. Okay, a base must produce what also? Okay, a base gives you OH minus, just like how an acid gives you H plus. But what do you need to add on the left-hand side to balance this equation out? You need to add water. Okay, so for base, right, you have no choice but to add water on the left-hand side. So you now have a few choices. You can add water on the left all the time and you will never go wrong. That's one option. If you guys don't want to think and just want to whack only, right, okay, then sure, just add water on the left-hand side. But if you are a little bit lazy for your acid, right, you can just dissociate the acid directly and it's still balanced. So it's up to you. Okay, let's write the Kb for this. How do you write the Kb? What over what? Products over reactants, right? So the products here is BH plus, the conjugate acid, over OH minus, over just B. Yes, okay, ignore water once again for the same reasons as just now. So stronger, higher Kb means stronger base, lower Kb means weaker base. Same properties as just now. It's not affected by concentration, so it's a good measure of strength. Okay? So we barely talked about bases, so I want you guys to write down one example from, actually we went through this example just now. Okay, but if this is NH3, can I dissociate this guy into NH2 minus? Is this legit? Then, is it one H plus different? Are they different by one H plus? Correct, right? But NH3 is an acid or base. Okay, if this is a base, then this one must be a Is it correct now? No, because what's the rule that we talked about? The acid must have one more H plus. Okay, so from NH3, this one should be NH4 plus. So that's how you probably didn't notice because the equation was already given to you. So it really depends on, don't just take away H plus all the time. Follow the rules, you'll never go wrong. Okay, can? Okay, as for the balancing, you can balance this out also. Okay, what else do we need to add? It also must produce a OH minus, and you can see how it follows the same format as the generic format. Oh, good. Can I? Any questions so far? You can take down whatever you need to. Then for those who are ready, you can look at the question at the bottom of that page. In today's lesson is all about getting things straight. Next lesson is mostly math, a lot of calculations. Right? Okay, so we've been talking about weak acids, weak bases, weak. Okay, but are we going to talk about strong acids? I told you guys not much because it's an equilibrium topic. But let's wonder about this question. Do strong acids and strong bases have Ka or Kb values? Okay, I mean a strong acid can have a very high Ka one, right? A strong base could have a very high Kb. So is this correct? Okay, answer here is no, but you all know why that's the case? Why do strong acids and strong bases have no Ka or Kb? First of all, guys, when strong acids and strong bases dissociate, what arrow do they use? A full arrow. Does a full arrow have an equilibrium? No. So that's the answer. It's a very simple idea, right? They don't have it because strong acids and strong bases dissociate completely. So there's no equilibrium, right? As mentioned, all the capital Ks, the Ka, Kb, Kc, K whatever, this K stands for equilibrium constant. The word equilibrium is there already. And strong acids don't even have equilibrium, but so how does he have the right to have K or K? Right? Okay, no, cannot. All good? Can I? We'll go over one more equilibrium constant before we take a break. Okay, one more, very fast. Right? Can so far, right? Okay, let's take a look at page 10. We're going to cover 10 and 11, then we can take a break already. Okay, there's Ka for acid, Kb for base, but there actually is Kw for water. It's the most interesting one, okay, because they like to test Kw for a reason. Okay, so Kw stands for water, obviously. Okay, but let's come up with this equation first. Now, water is a very special compound. Water can actually dissociate into its ions by itself. You don't even need to add anything. You don't need to add a partner. It can just dissociate. Why is this so special? Number one, water is what kind of molecule? Ionic or covalent? Water is clearly covalent, right? Can covalent compounds produce ions? That's weird, right? Okay, that's why water is weird. Okay, water is special. So this is also known as auto-ionization. In other words, water can actually ionize automatically. It's not a special term or anything. To produce H plus and OH minus. Somehow it can do this. Okay, we just need to accept that it can. And because of that, right, it can actually have its own equilibrium constant. Because it only dissociates partially. So there's an equilibrium. So guys, what's the formula here? Same thing. Products over reactants, right? So the products here are H plus, OH minus, over. Do we over the water? No. Once again, water is pretty much a very high concentration. It is a constant. We don't put it inside the expression. So you have learned this in a few times. Okay, we have learned this as the ionic product of water. Okay, so that's it. Right, a few numbers here and there. Guys, you see, If I were to add a negative log at kW, so it becomes pkW, then what's the formula now? Logarithms. Logarithms will now become addition, right, over here. So it becomes PHN plus POH. Do you all remember from earlier, pH plus POH equals to what? 14. But is it always 14? Only at room temperature. Okay, these values in mind are very important. For now, we're going to discuss room temperature. Yes, okay, fine. So guys, pH plus POH equals to 14. What is 14? 14 is actually the ionic product of water. In other words, okay, the kW of water is 1 times 10 to the power minus 14. Just do a simple conversion here. That's a conversion. And so far. Now, this is a constant that you need to remember, but don't worry, it is not difficult to remember. That's number one. And in the event when you forget it, it's in the data booklet. Most of our calculations will be based off this. So yes, room temperature. And okay, that's like the basics so far. Again, guys, if I change the concentration of H plus or OH minus, does kW change? No. Just like all the other capital Ks, not affected by concentration. Okay, so once again, not affected by concentration, only affected by what? Temperature. Okay, bear this in mind. pKW only affected by temperature. So that's why 14 can change to like 13, 12, 15, 16. Okay, depending on how hot your water is, basically. All good so far? So, you can now write this down. Okay, whatever, write down on the board. Okay, we're going to understand the idea of neutral. What does neutral or neutrality mean? Okay, guys, when I to tell you neutral, what do you all think of? pH 7. Okay, good. Okay, so this is what we thought. Why 7? Have you ever wondered why it's 7 and not 6 or 5 or 10? Any guesses? Any smart guesses? Yeah? Okay, so you all say that it's in the middle of 1 to 14, right? Okay, let's write that down first. Okay, middle of 1 to 14. Okay, so because you guys have learned that pH ranges from 1 to 14, okay, fair enough. Okay, we're going to investigate whether pH 7 really means neutral or not. Let me present to you an experiment. So, scientists, what they've done is this. They took 3 cups of water. The first cup is cold, about 10 degrees, okay, cold water. The second cup is, okay, room temperature, lukewarm, right? The third cup is hot, so about 50, let's say about 50 degrees. And what they did is they go and measure the pH of the water. So the pH of the water here, they go and use some sort of apparatus. They call it a pH meter. Very cool one. They go and dip it in, then the thing will read out the pH. So nothing on now. Okay, so it's just this. Now they measure the room temperature water first. Okay, sure enough, it's 7. Okay, but they measure the cold water, it's somehow 7.5. They measure the hot water, it is 6.5. Okay. Okay, don't write anything in the notes yet. I know the notes are later I'll tell you what to do. Just look at the scenario first. Okay, when you see the pH of water is 7.5, what will you think of? The water is now what? Alkaline. Okay, when you see 6.5, you tell yourself the water is. Okay, guys, you think about this again. Can a hot water suddenly become acidic? Because such thing, you drink hot water, is it sour? No, right? Okay, you drink cold water, is it bitter? No. So guys, if you drink cold water and hot water, it still tastes like water, right? Normal. What does that tell you? That water at whatever temperature must be neutral. Okay, so let's take note first. Water, we can establish, is always neutral. Let's not get fooled by these numbers. Okay, it's not that, oh, suddenly, wow, water is acidic. No, okay, we know it's neutral for a fact. Let's be grounded with our beliefs here. Then what does that mean? Neutral, neutral, neutral. So does pH 7 really mean neutral? No, it's not conclusive. For some reason, based on the experimental data, 7.5 and 6.5 could be neutral as well. So what is neutral? It's not pH 7, clearly. Is there another idea towards neutrality? Like for example, guys, what is neutral, right? Okay, if I have 1H plus how much OH minus do I need to neutralize the H plus? You need one OH minus. If I have 4 H plus, how many OH minus do I need? You get the idea. So what is neutral? Is there some sort of formula that we can use now? H plus and OH minus must be equal. Can see that? So we have come up with a more reliable way of understanding neutrality. Neutral means H plus and OH minus concentration must be equal. Take note of this. So as I said at the start of the lesson, we are going to start to dispel some of the things we have learned in secondary school. One example is this: pH7 is not neutral. Get that out of your head from now on. So the first fact is this: pH7 is not neutral. Second fact, water is always neutral. Always stay grounded with this fact here. Don't let the MCQ option sway your beliefs. Okay, it's always neutral. So take a look at it. Now this will bring us to another idea. Okay, so just now I did mention this. You all know 7 because it's in the middle of 1 to 14. Why? Why in the middle? What's so special about being in the middle? Okay, look at this equation again. When the pH, okay, at room temperature, it is at 7. What is pOH? Also 7. So there's a reason why it's in the middle, right? It's in the middle, so what? So that pH is equal to pOH. Then that is neutral. So let's write down another column here of pKW. So we already determined that it's 14. Why? 7 plus 7. Can you all fill in these two values? What's this? 15. At 50 degrees, what's the pKW? And does this make sense? Yes, because we already know that pKW is affected by temperature. It's only 14 at 25 degrees Celsius. It can change. You do not need to memorize all these numbers. Okay, in the notes, there's a table. Yes, I know. But you do not need to memorize the KW values. That's ridiculous. You only need to memorize the room temperature value. Why is that the case? Because in the exam, they'll give you a graph of some sort. They'll give you a graph or values. Okay, so no need to scatter. Right, you can see this so far. So with this idea, can you all take a look at page 11, the very bottom? Go and fill in the table. You should know how to fill this up already. And then we'll fill up the box. I'll tell you how to fill up the middle box. Okay. So the middle box asks this question: is the neutral pH of water at 10 degrees still is 7? Okay, so I'll put all this into a very nice box to revise. Okay, so I'm going to write down 2 scenarios: the correct scenario and the wrong scenario. Okay, sometimes you all need to write wrong scenarios down to really bring out why the correct scenario is correct. Right? Okay, so what do I mean by that? Let's write the wrong scenario first. So we have this formula: pKW equals to pH plus pOH. Now, guys, again, at 10 degrees, what is the pKW from your table at the bottom of the page? Okay, it's right there. It's 14.5. Again, this is given. So this is at 10 degrees Celsius. So guys, if the neutral pH was indeed at 7, okay, so let's just pretend the statement is correct. If the neutral pH was 7, then what is the pOH? And math, right? 7.5. Are they equal? Are they neutral? No. Okay, so if the neutral pH is 7 degrees, pH is not equal to pOH, so it's not neutral. In fact, guys, at 10 degrees, if the pH was 7, the water is what? Acidic. So guys, now can you see, okay, the pH 7 water is actually acidic. Then that's not water anymore, right? Because water, again, must be neutral. This is something else already. Some don't know what. Okay, so it's not neutral. They can maybe put a little, in fact, this thing is acidic. I write thing now because it's not water. Please don't get confused here. Then now let's write down the correct example to really bring across the idea here. Okay, pKw is pH plus pOH. You get 14.5, but this is only at 10 degrees. So what is the neutral pH? Okay, so you just need to divide by 2, right? Okay, I've already gotten the idea. Neutral pH is equal to 7.25, so that pH is equal to pOH. Then this is water, where it's neutral. Okay, you all can see from the map. Okay. Okay, all good. We shall take a break first. Okay, until 12:20, so 5 minutes. Okay, then we'll do a page regarding the neutral or not neutral. Okay, so take a break first. Okay, anyways, let's continue. Okay, so later on we'll do some calculations. So from now to the end, there's not much new concepts already. Okay, but let's finish up page 12. Okay, because on page 12, it's the neutrality thing. So just go and tell me whether each statement is true or false. Okay, they ask you guys to refer to the data on the previous page. Okay, so you all see the statements. On the previous page, you see all the values at the bottom, right? You kind of need to use that for this page. So it's like a mini exercise. Yeah, okay, so just give it a try. You want to explain a little bit. Okay, the only question that needs explaining is pretty much just part A. So you can use the box for that, right? B, C, D, E, you just tell me true or false. Okay, don't really need to justify. Yeah, I think you guys are mostly done, right? Okay, main question I want to go over is part A, because sometimes part A they can justify it. Okay. Part A they can change it a little bit, and we will see how they frame it up. Okay, so for part A it's true. Okay, but why? This is endothermic. From just this equation, you can tell why already. Any idea? Okay, endothermic reactions have a few features, right? And this just happens to fulfill one of those features. What happens in this process? Bonds are being broken. Yes, that's it. Okay, so you can see the only thing happening here is bond breaking. Now, highlight in the question, they say ionic dissociation. Okay, if they were to say ionic formation, that means this should be the backward reaction. Now, of course, we have learned enthalpy changes before. If the forward is endothermic, the backward must be exothermic, opposite processes. In this case, you just need to tell me, ionic dissociation water is the bond-breaking process. So it is endothermic. But because there's a lot of space in the box, okay, let's write down an alternative question. Okay. Now that we have established that this is a bond-breaking endothermic process, we can answer part 2 of this question. Does Kw increase or decrease when temperature increases? Come, let's discuss. The format of answering this question is by using Le Chatelier's principle. So in the question, they could say, explain using Le Chatelier's principle what happens to blah, blah, blah. Okay? So first of all, guys, now that we understand that it's endothermic in the forward reaction, when temperature increases, does it favor the forward or backward reaction? Recall the Chatelier's principle. If you increase the temperature, what does the system want to do? Increase or decrease the temperature? Decrease. He wants to do whatever you do, but the opposite. He wants to counter you. He's like a rebellious kid. So if you increase temperature, he must favor forward or backward. Notice this, forward reaction is endothermic. Backward reaction is exothermic. Now we should know from our features, endothermic is cold or hot. Cold. So in other words, when you endothermic, right, the temperature will drop. Exothermic is hot reactions, temperature will increase. So if you increase the temperature, what does he want to do? He wants to favor the forward endothermic reaction because you will reduce that temperature. So you can tell me this, the forward endothermic reaction is favored to absorb heat. Because guys, you must write to absorb heat because that's the only way to offset your increase in temperature. Okay? Right? Forward reaction favored to absorb heat. So guys, where does the position of equilibrium shift towards? Forward endo is favored. So forward means shift to the right. So when POE shifts right, what happens to your H plus and OH minus? Okay, increase. Your concentration of H plus and OH minus increases. And what are we trying to answer? We are trying to answer KW. Guys, we have gotten all the way until this point. What happens to KW? Increase or decrease? Remember the formula for KW is just H plus times OH minus. So it's what? Increase. Okay? So concentration increase, KW increase. But wait, I thought I already said that concentration doesn't affect KW. But over here, can you see the temperature changes? Okay, so if temperature change, yes, is an exception. You will allow it to increase also. So this is a very common question. But you must first establish this endothermic. If you can't establish the first part, then I'm sorry, you can't really determine the second part. Okay, good so far. Okay, part A done. Let's look at part B, C, and D. Part B is true, part C is also true. Why? Let me ask you guys a few questions. When you heat water, concentration of H plus increase, but does it mean water becomes more acidic? No, water is what? No matter what. Neutral. But when H plus increase, then why is it neutral? Why is it neutral? Because is H plus the only thing increasing? No, OH minus increases also. Can see that? If one increase, the other must increase as well. They have to increase by the same extent such that they are still equal. That's the definition of neutrality that we've already discussed. So don't let the statement confuse you. Okay, Ken? So B and C come hand in hand, they are correct. Is D correct? Okay, we understand A, B, and C very clearly. D is 100% wrong. Because why? The clue here is pure water, right? Pure water must be neutral, must be equal. Doesn't matter what temperature it is, it's going to be equal. Okay? How about part E? Part E, there's no concept involved. You just need to look at the table on the previous page. Okay, at temperatures higher than 25 degrees, what's the pH? At temperatures higher than 25, the pH is all smaller than 7, right? Based on your own calculations. Okay, can. So E is wrong. So, any questions here? No? Right, we're gonna look at the next part. Okay, the next part, we're gonna just finish this up with two more short little information and then we can practice calculations really. Okay, page 30, sorry, page 13. Okay, so Ka and Kb and Kw, right, can all be linked via this formula. Ka times Kb give you Kw. Okay, as for how I derive this equation, you take a look at Kw. Kw is fundamentally H plus and OH minus. I can show you guys very quickly, you don't need to take this down. But when you take Ka times Kb, right, you eventually simplify to this. How? Take note, this Ka times Kb, right, must be for a conjugate acid-base pair. Remember the relationship between a conjugate acid-base pair? They have to differ by one H plus. And the acid has the extra H plus. So when I mean conjugate acid-base pairs in this, for this formula, it must be for something like this: NH3N, NH4 plus, or CH3CO2H and CH3CO2 minus. You can only differ by one H plus. It cannot be some random acid at base. So for example, if you give me CH3CO2H, and then suddenly you give me NH3. I know this is an acid, I know this is a base, but you cannot use this equation to link them up together because they're not related. They're not even partners. How do you relate them together if they're not even related in the first place? Right? Okay, so that's the logic. They have to be related first. Okay, how does this work? Okay, let me just give you all an equation. For Ka, okay, let me write this here actually. Okay, for the acid, when it dissociates in water, it gives me CH3CO2 minus H plus. Agree? Then my Ka is just products over reactants. If you want to take this down for your own info, go ahead as well. There's no understanding here. They won't test on this. Okay, in the exam, you just need to apply this formula inside. Okay, but for Kb, the Kb, who is the base? The base is this guy, agree? Let's try to write down this guy's dissociation. So when C3CO2 minus, you dissociate water, what will you form? This is the base. What will you form? Conjugate acid, right? What's the formula? One extra H plus, good. So CH3CO2H. Can you see, right? They are like always together. They are never apart. Okay. Right? Okay. And what's the other thing? OH minus. So yes, you could take the base, right, and dissociate it in water also. This one you will see more in the next lesson. Okay, but if you write the base, if you write the Kb, it will be just products over reactants once again. Ignore water for obvious reasons. And guys, just by doing this, can I multiply Ka and Kb together? Can, right? What will happen? Cancel, 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 cancel. So I have H plus OH minus at the end of the day. So it still works, but it only works if it's for a conjugate acid-base pair only. Okay? You take this down actually, I feel that maybe it's better. You all can understand this when you revise. But this will help us to understand one thing that I went through just now. Right? So with that, let me just write this equation too. Okay, we take a look, right? Okay, I'll leave this here first. Okay, I'll talk about the next thing regarding this formula. Remember I said just now, if you have a weak acid, you will form a what? The conjugate base will be strong or weak? strong conjugate base. Vice versa, if you have a strong acid, you will get a weak conjugate base. Why? Okay, we're trying to understand why they are opposites of each other. It's because, guys, of this formula here. Kw is for water. For a fixed temperature, the Kw must be a constant. Now, with a weak acid, your Ka must be high or low. Weak acid. Weak acid must have a low Ka, right? If you have a low Ka, Kb must be high. In order to ensure that Kw is a constant. Can you see that? It's like a seesaw, it's trying to balance itself out. So a high Kb means it's a strong conjugate base. Vice versa for this, but then this is not a very good example because HCl is a strong acid, and as I mentioned, strong acid shouldn't use Ka or Kb, so let's not talk about that. Okay, can? Yeah, okay, that's for this formula here. You will see how this formula is applied in the next lesson. Okay. At the bottom of page 13, there's something very simple there called degree of dissociation. Now, this one here is not that important because it's just how much it dissociates, right? So it's just a percentage, just a fraction. So as I mentioned just now, okay, there's an example I use 10% dissociated. So 10% is the degree of dissociation. It's not really nothing much. Later we'll apply that in our question. That's more obvious. Okay, now we have to do this exercise next. Take a look at page 14. Okay, on page 14, look at this exercise here. We have to write down the equations for all of them, all the dissociation equations on page 14. Again, as I mentioned just now, if you remember the rules for a conjugate acid-base pair, you will never go wrong. It doesn't matter what they throw at you. So give it a try. Some of them you might not know what it is, so they clarified it at the side. So are they a weak acid or weak base or whatever? Okay, when you give this try. Let's write down some of the obvious answers first. Go and identify the acid conjugate base pair as well. Okay, can. Acid conjugate base, acid conjugate base, acid conjugate base, last one here. Very simple. Okay. I'm gonna not talk about D and F yet. You can check the rest of your answers. Okay, specifically part B. Part B, right? Yes. Okay, you probably never seen what is OCl minus before, but it does exist. Okay, it should by right be ClO minus for your own information. They will usually write it in this format. But because you're breaking apart the H from O, okay, by the way, HOCl looks like this. You're breaking the H away from the O, that's why the O now ends up with the minus charge. That's why I specifically put the minus on O and not Cl. So if you get it wrong, never mind. I don't expect you guys to know what this guy looks like. Okay, but just change the minus to be on O or you flip it around like this. Okay, okay. The bottom line of this exercise is no matter what they throw at you, just follow the rules that you say. So taking a look at part D. Guys, part D, they already said this is a base, right? N is the base, the weak base. So how? Can you just tell me what the product looks like first? If this is the base, you're gonna get a conjugate acid. How should I draw the conjugate acid? What should I modify that compound to look like? Add a H plus to the anywhere. Where should I add a H plus? Now they purposely say that N is the base, right? So just add a H plus here. Now don't draw a bond. Just put a H plus on top because if you draw a bond, it is wrong. This N has a lone pair of electrons, and this lone pair is datively bonded to the H plus. I say again, H plus has no electrons, N has a lone pair of electrons. So he's literally just giving. He is giving. Okay, so if you have to draw a bond, it has to be a dative bond, or you can just don't draw any bonds at all to be safe. Now, guys, what theory does this remind you of? Electron given to the H plus. What theory is this? Lewis theory, right? But does this have any other theories involved? A set H plus. So what theory is this? Bronsted also. So guys, can you all see this example specifically has two theories in place. Okay, balance out the rest with OH minus and water. Go ahead and maybe highlight part D and write this down. Okay, so the lone pair of electrons on nitrogen is donated to the H plus. In other words, this is a dative bond. And in other words, this is a Lewis acid-base reaction. But at the same time, because there's a transfer of protons, so put another separate point, the transfer of protons, H plus, also implies there is the Bronsted theory involved. So in your, sometimes when they can ask like what are the theories involved, right? You need to tell me both, right? Or usually they ask you what theory is involved. If you tell me either, it is both correct. Okay. Okay, let's finally look at the last one. Okay, they told you guys the last one is a weak base. So over here, this is the species. Remember, don't remove the H plus because this is a base. So you get the acid must have the extra H plus, so it becomes NH3 plus. So D and F quite important. Can you see the answer for F? Anyone cannot get this? Okay. Can just add the H plus, extra H plus. All good? Okay, this, right? Now, because of time constraints, right, I'm gonna skip 15 and 16, and for good reason. Because 15 and 16 is about calculations of strong acids and strong bases. Okay, it's you can do this yourself, obviously. Okay, but you don't need to do this because, as I already mentioned, they will not test you guys on strong acids and strong bases in exams. But very rarely will they test you on that. Because there are better things to test you on. And what better things to test you on? Weak acids, where there's equilibriums to tackle. Okay, so 16 and 17, sorry, 15 and 16 not important. Turn over to page 18. We're going to look at the first calculation question type in this topic. There are, as I already warned you guys, there's a lot of calculations in this topic. It's just that in today's lesson, you're just learning the basics. We are going to look at the first calculation type called dissociation. Next lesson, we're going to look at two more calculation types. You guys might have heard of it before, salt hydrolysis and buffer. Okay, but if not, dissociation first. Okay, now look at this first equation, the first question here, sorry, page 18. There are three steps to a dissociation question. The very first step for every calculation in this topic is to write down an equation. If you don't write a chemical equation, okay, we can't really do anything. Here's dissociation, so dissociation equation. Can you all read this question here and give me the dissociation equation for this species? Okay, can. Ethanoic acid, okay, not very difficult here. Okay, they gave Ka value also, they gave the initial concentration. All fine with that, right? Okay, it's right here, okay, it's the one that we did just now. So next step, I want you guys to give me an IC table. This table here, eventually we can phase this out, but because we're learning this for the first time, we need to understand the process. Eventually, I'll teach you guys the shortcut to calculate this question. This question actually can be done within one formula, but not yet. Okay. Last but not least, right, after we have done all our IC table, we can sub the equilibrium values. Okay, we can sub the equilibrium E into your Ka expression. Because again, do not sub anything else into your Ka. Ka is an equilibrium constant, so you can only sub equilibrium values. Okay, with that? Now, can you all fill up this? Okay, let's fill up this table together. What's the initial concentration? 0.1. What's the initial concentrations of the ions? Okay, 0. Okay, good. What's important here is the change, guys. How much of the acid dissociated do we know? Okay, this is a weak acid, right? We just know it doesn't dissociate completely, but it does dissociate to a certain extent. So we can only put a unknown X. Okay, we dissociate by X, okay, then we can fill out the rest. Okay, how much over here? Also plus X, because you follow the mole ratio, it's 1-to-1 mole ratio. So IC table, very, very straightforward. Can see the logic behind it. We do not know how much it dissociates, so we give an unknown width first. And we have the equilibrium values, right? These equilibrium values can now be substituted into your Ka expression. Guys, then what is your Ka expression? Products over reactants, right? Okay, so products, we have both of these guys, which is X squared, over the reactants, which is just the left side, 0.1 minus X. Okay, so far. However, there's one little thing that we need to do first before we can perform our calculations. As you can see here, this is a quadratic equation. Now, I know it's possible to calculate it with your GC or whatever, but don't do that in exam. They will not accept quadratic in chemistry. So we're going to get rid of the quadratic equation. And we're not just going to get rid of it for fun. Okay, guys, can I ask you a simple question? The value of X compared to 0.1, is it small or big? Very small. Because as we already determined, weak acid dissociates only to a very tiny extent. But because it is so small compared to 0.1, we can effectively ignore it. Agree? 0.1 minus a small value is pretty much just 0.1. It's not going to have a big impact on our final answer. So that's why we are able to just assume that 0.1 minus X and 0.1 are the same thing. We can justify ourselves by saying this. we assume that x is a much smaller value than 0.1. See, I put two arrow signs there to really get across that idea. Then now you can equate this to the value of Ka, which is what is already given to you guys. And I want you all to solve for x. Because by solving for x, you can find whatever the question is asking for. Okay, there's two parts to this question. We're going to finish this up. Right? Here, value of x should be this. Okay, but what does this value of x even represent? What are you even calculating? That's the question. X represents what? Yes, okay, so the question is asking for pH. And you notice that pH is a measure of pH plus. So just that's x. Okay, so this is the concentration of pH plus. In order to find pH, just apply your equations, your formula, and get the answer at the top right. Okay, that. So this is the answer for part A. Okay, they also want for part B. Okay, guys, how do you get the answer for part B? They're asking for the degree of dissociation. Okay, so how much the acid dissociated? So can I ask you a question here? How much of the acid actually dissociated? 0.1 x or 0.1 minus x? Which value should we use? Just x, right? This is the amount dissociated, agree? So this degree of dissociation can be expressed using alpha, it's just a symbol. So what's the formula here? It's however much that dissociated, which is x, or whatever we found for the value of x, divided by what? Okay, the total, right? The initial. Okay, so do this. And then you want to multiply by 100, go ahead. Okay, it doesn't really matter. So the answer here is this. About 1.34%, if you times 100, it's 1.34% of the acid dissociated. Just based on this value, is it a strong or weak acid? Weak as hell, right? Okay, so that's the answer. Okay, extent of dissociation. As I said just now, strength refers to the extent. We have one last question. Can you all go over to the next page? Yeah, I know there are two questions now. Okay, but we're going to do question 2 only. Question 3, you can try yourself. Okay, question 2 is similar to question 1. Follow the steps. I need you all to try the question yourself. Right? Okay, then we'll be done for today. Okay, they're even nice enough to give you the equation. Okay, so copy it out again. Okay, some of you may realize if you were to use the same method as just now, you will not get the answer. Right? Okay, so I see most of your tables, you use the X method. Okay, but actually, guys, go and modify the table. Okay, I know with the X method, you might still get the answer. But in this question, right, the information they've given you is a bit different. Okay, so you realize something, okay, water you can ignore in the IC table. Okay, this is the initial concentrations. You guys mostly did this, okay, 0.2 minus X plus X plus X. Now I'm going to show you guys why this table here is a bit pointless. Because if you were to substitute the equilibrium values into your KB, you'll get something like this, right? Now, even after assuming the X is nothing, what do you notice about this question? Can you find the KB? Did they give you the KB value? No. If we do not know what the KB value is, how can we find X? So we have two unknowns in this question, right? However, the question did tell us what the pH of this is. The pH of caffeine is 11.5. That's the only information, only other information they've given us. But we already know that X is not a good method for this question. So somehow we need to use 11.5 to figure out how to calculate this. What can we find just from pH 11.5? What can we use it? Okay, good. Why do we find pOH? Why? Because this question here is giving us OH minus, correct? So why do we need to find P? Why do we need H plus? We don't need H plus, but we need OH minus. How do we convert pH into pOH? Is there some sort of formula we can use? Okay, we can take 14 minus 11.5, right, the pH. So we can get a pH of pOH of 2.5. Let's see that. Again, we must do this conversion because we are only interested in OH minus from this question. So guys, pOH is 2.5. Can I find the concentration of OH minus? Which is what? How do I find concentration? 10 to the power of negative 2.5. You can calculate that, or I can just leave it like that first. Can you guys see that this is the concentration of OH minus at equilibrium? It's after the dissociation, because at the start, you do not have any OH minus. After the dissociation, it is this value over here. So that's why this question is slightly different, but honestly, the rest of it is the same. If this is the equilibrium concentration, then what's my change? Same thing, right? Okay, I have to plus 10 to the power of negative 2.5. Here also plus, and here is minus. So I can basically fill out the rest of this table. As you can see, this table doesn't use X at all. Do not use X in this table. Please go and modify it. I know you can still get the final answer, yes. Okay. But I feel that this is a lot more important because there's another issue that might arise. Okay, can you all get this one? Okay. Now, they want us to calculate KB. So come, let's calculate KB here. All you need to do is to substitute the equilibrium values into my KB expression. So this is 2.5 squared, 0.2 minus 10 to the power of negative 2.5. Should get the final answer written at the top right. Now guys, why I want you all to change the table is because if your table has X, I'm afraid that you guys might do this. 0.2 minus X, you can assume it's just 0.2. Is there a need to do that in this question? Do we need to get rid of any quadratic here? Answer is no. Because in this question, I have all the values in place. If I have all the values, please do not assume this to be just 0.2. You must minus away how much that dissociated. A lot of people tend to forget to minus this off, and then they end up wrong. Okay, it cannot be 0.2 because it must have dissociated to a small extent. Can you all notice this? Okay, please take note. I'm going to highlight this part. Okay, if it's not X, you must minus off the actual value. Only when it is X, then you have the excuse to assume away the X. Got it so far? Okay. Both of these questions are the same. Please do not get me wrong here. It is the same exact question, but they just give you different information to find different things. This is the opposite of the first question. I hope you all realize that. And then you must know when to use the X, the table or not. With that said, any questions? No? Okay, if not, that's all for today. Okay, Right. Please go back before next lesson. I say this with utmost importance. Please at least read through whatever we did this lesson. Because guys, when you all revise this topic, you're not going to revise the first couple of pages, all the basics. That one will be already in your head. Right. Next lesson, if you guys forget about the fundamentals, right, it's going to be hard for me to proceed. So please look through one day before. Okay, I'm not asking for much. One day before, look through the notes again, whatever we've done so far. Right. Then the lesson will be a lot easier for you guys also. Okay, can? Right, okay, so that's it.